Hello, I am Shoumik Maiti. I am an online student of ECE 658 Internet Engineering class. I will be making a presentation on Universal Serial Bus USB. I am sure all of you have used USB for connecting peripherals to your laptop or transferring data from your laptop to portable hard drives or cell phone or even charging cell phone. USB is a very popular serial interface that is used for connecting a wide variety of peripherals to the PC, and it has been widely adopted in the industry. If you are working as a chip design engineer or a embedded systems design engineer, I'm sure you will come across USB in some form or the other, and having a knowledge about how USB works will be very helpful. I have also included my email in the front page of the presentation, so please feel free to contact me if you have any questions. This is the outline of the presentation. I will be discussing about the motivation of developing USB and its evolution over the last 20 years. I'll be describing the architecture of USB and how the USB system is partitioned into the hardware and software. I'll be going over the cables and connectors used in USB, the signaling and power delivery feature of USB, and also describing the USB physical and the link layers, and also going over the USB protocol and how the data transfer takes place in form of packets between the host and the devices, and also touch upon the future trends in USB and how it compares with other competing technologies. USB was developed by a consortium of companies that comprised of Intel and Microsoft as a low-cost standard PC to peripheral interface, and the standard interface expedited the development of creative peripherals. Before the advent of USB, there was not a standard interface that could help connect various kinds of peripherals to the PC, and that was a huge problem. And also expanding ports of a PC was difficult, but this all became possible and very easy with USB. USB is also very easy to use and can be used by the novice user, and it supports many kinds of devices. One of the very important feature of USB is the plug and play feature. So here any peripheral can be connected or disconnected on the fly without damaging the peripheral or the PC, and it also has automatic enumeration where the operating system can detect what kind of device is attached and load the appropriate device. USB was first introduced in 1995 as USB 1.0, and then it became standardized as USB 1.1 in 1998. The first version of USB came with 2 speed of data transfer in the bus. The first one is the low speed data transfer, which is 1.5 megabits per second and was developed to connect keyboard, mice and gaming peripherals to the PC. Next data rate is full speed USB, which is 12 megabits per second and was used to connect phones, audio devices and to transfer compressed video. The next evolution was USB 2.0, which became highly popular, and it supports data rate up to 480 megabit per second and can be used for video, imaging or storage devices where a large amount of data transfer takes place. With the evolution of technology and technology scaling and Moore's law, there were new kinds of data or media that was developed, like HD media, and also the portable hard drives became large enough that it can store up to terabytes of data. So this all required a much faster a serial interface, and USB 3.0 was developed in 2008, and it supports speed up to 5 gigabits per second and is called super speed USB. So this is a comparison of how much time the same data transfer will take across the various generations of USB. Say 1 GB of data to be transferred to a flash drive can take up to 22 minutes on USB 1.1, 33 seconds in USB 2.0, and 3.3 seconds in USB 3.0. And say a more current example, like a HD movie, which is like 27 gigabytes, and it can take up to 9.3 hours to download using USB 1.1, and is not very useful. So it shows how relevant USB 3.0 today is, which can do the same transfer in 70 seconds. It should be noted here, though USB has evolved a long way from USB 1.1 to 3.0, all the USB specification is backward compatible. So a USB 3.0 host can work seamlessly when connected with a USB 1.1 device. And we will actually go over how the design of USB is done to maintain this backward compatibility, and this is a very useful feature of USB. Some main points about the USB bus architecture. USB is host controlled. There is only one host in the USB bus, and multiple peripherals can be connected using a tiered architecture similar to Ethernet, and the hubs allow the connection of multiple peripherals to the same host. The hubs are actually devices that repeats the data, upstream data, to the downstream devices, and also the data from the downstream devices to the upstream ports, and help connect multiple devices on the same bus. As mentioned, that the host is the master of the bus and devices are slaves, and each device is assigned a unique address by the host. And whenever it receives any data which is broadcast in the USB bus addressed to it, the device responds to that request. It should be noted here that USB 2.0 is a half duplex bus, where both the transmit and receive happens on the same wires. So the transmit and receive is time division multiplexed, and all the USB transfers have to happen in a certain time period. That is, the devices have to respond within a fixed interval of time to avoid collision. USB uses a 7-bit addressing scheme for the devices, so it can support up to 127 peripherals. The address 0 is a special address, and it is used by the devices which has not been assigned a unique address before enumeration. And there could be 5 levels of hubs, which is limited by the timing of the bus. Now, the USB interface is abstracted into 3 layers. The first layer is called the USB bus interface layer. It provides the physical connection and the electrical signaling, and this is accomplished by specialized hardware of the USB 5 and the controller. The next layer of abstraction is the USB device layer. This is comprised of the system software in the OS for performing general USB functions. And finally, the application or the function layer, which is made up of specialized application software to support the unique device functionality. So across the various generations of USB, there were several different controllers that has been standardized. The first one is UHCI, the Universal Host Controller Interface, which was licensed by Intel, and implements most of the functionality in software. And OHCI is also for USB 1.1, developed by Compaq, Microsoft, and National, and most of the functionality is implemented in hardware. With the evolution of USB 2.0, the EHCI, the Extended Host Controller Interface, was created, and this supports the USB 2.0 functionality, and this works in conjunction with UHCI or OHCI. And finally, the latest USB host controller is XHCI. This is also developed by Intel, and it is a unified architecture supporting USB 3.0, USB 2.0, as well as USB 1.1. It is optimized for 5 gigabit per second, and it has a lot of power management features, which is becoming increasingly relevant as USB is being used in embedded devices which are battery powered, and energy and power is of utmost importance in those devices. And also XHCI supports virtualization. The same USB port could be shared by different virtual machines running on a server that is implemented using XHCI. And more on the system partitioning, most of the physical layer, which is the port and its functionality and the controller, is in the hardware. And then we have the software stack, which comprises of the host controller device driver. This basically abstracts the hardware to the OS. The OS doesn't need to know which controller is implemented, and it uses a very similar interface for doing the USB functions. Then it is the USB driver, which is part of the OS. And above that we have class drivers, which are specialized drivers for different classes of USB devices. We will be covering the USB driver device classes later. And finally, the application software, which is responsible for implementing the device specific USB functionality. A little bit details on the USB cables and connectors. The type A connectors and receptacles are used on the host side, and the type B connectors and receptacles are used on the device side. With more and more penetration of USB into devices of smaller form factors, there are other smaller receptacles and connectors like mini and micro USB were developed. And as you are seeing that most of the cell phones currently use a micro USB connector, and I'm sure you're familiar with it. The USB uses a twisted pair for its data lines. It uses 2 lines for differential data signaling, which is D plus and D minus. It also has a power line in the bus, and this is a unique feature of USB, where we can deliver power to the peripherals also using the same bus. It has an ID pin which demarcates the host and the device, and mostly used in USB OTG specification, where the role of the host and device can be dynamically determined, and also has a ground line. The USB cable is limited to be 5 meters for a full speed and high speed configuration. The USB 3.0 actually is full duplex, so it has separate line for transmit, which RX plus and RX minus, and separate lines for receive. It's RX plus and RX minus, and transmit TX plus and TX minus. And the receptacles and the connectors are designed in such a way that it supports both USB backward compatibility. So a USB 3.0 receptacle and connector can also be used to work with USB 2.0 functionality, and same case for the USB cable. that helps to implement the backward compatibility. We'll also come to the architecture of the transceiver, how it helps in the backward compatibility too later in the presentation. Little details on the USB signaling on the bus. USB uses differential signaling, and that helps to cancel the common mode noise. The full speed and low speed nominal voltage is 3.3 volt. The logic 0 is implemented as a low level signaling, and logic 1 is implemented as a high level signaling from 2.8 volt to 3.6 volts. The high speed and super speed uses also differential signaling, but with a less swing to conserve power. And minus 10 volts to minus 10 millivolts to 10 millivolts is used for logic 0, and 360 millivolts to 440 millivolts is used for logic 1, the nominal voltage being 400 millivolt. USB also mandates that the PLL jitter be bounded to 500 ppm for the high speed connections, and it can go up to 15,000 ppm to for low speed connections. This relaxed requirement of PLL jitter in the low speed mode actually helps in replacing costly crystals with resonators and develop low cost peripherals, which is very common in USB. If you're not aware of what this ppm means, it is parts per million, and this actually gives the maximum jitter that could be supported in the USB system. The USB has another unique functionality where it can supply the power to the peripheral. So the USB peripherals could either be bus powered or self powered. Now bus powered peripherals go through a power negotiation step where they program how much power that it can draw from the V-bus. The low power devices can draw at most of 100 milliamp from the V-bus, and the high power devices can go up to 500 milliamp from V-bus. And in the newer versions of USB 3.1 and power delivery, it supports up to 100 watts of power, where very high powered devices can also be powered using the USB bus, and this feature comes in very handy. It should be noted here that self-powered devices should be careful when turning on the power. The power should be removed when V-bus is turned off, so that there is no potential damage done to the host. And as most of you must be using USB for charging the cell phone battery, and this also uses the same V-bus for power supply while charging the battery in the cell phone. A couple of terminologies we want to get familiar with before we discuss some more details of the specification. The differential one is like D plus is high and D minus is low. The differential 0 is D plus is low, D minus is high. And this is single-ended signaling called SE0, single-ended 0, where both the lines are low. And J state. J state is like the idle state in the bus, and for high speed it is differential 1, for full speed it is differential 1, for low speed it is differential 0, and K state is the opposite of the idle state, where it is differential 0 for high speed and full speed, and for low speed it is differential 1. And there are specific characters for start of packet and end of packet. A start of packet is done by switching from idle state to K state. That's from a J state to K state, and the end of packet is demarcated by SE0 followed by 2 bits of J. Here we see the USB transceiver on the left. This is the USB 2 transceiver. As you can see, there are separate circuitry for high speed, this is the high speed transmitter, this is the low speed full speed transmitter, and this is the high speed receiver, and this is the low speed and full speed receiver. So this also this architecture also helps to maintain the backward compatibility. If the device is only low speed and high speed capable, it just has the low speed and full speed transmitter and low speed and full speed receiver. The high speed part is not there. Similarly, for super speed, this also works as a parallel feature in parallel to other speeds of operations. So if a device does not have super speed, doesn't need to include the super speed circuitry, but if it has super speed, it has to include the super speed circuitry and also support the lower speed modes. Okay, as we discussed that, it's kind of amazing that in USB various speed devices can get connected to the same socket, same USB receptacle. So there has to be a way by which the USB system identifies the speed of the device when it gets connected. To help identify the speed of the device, the low speed and full speed devices have a pull-up on their data lines. The full speed device has a pull-up on the D plus line. So when a full speed device gets connected, the D plus line is pulled high to 3.3 volts, and the host detects this 3.3 volt on the D plus line to infer that a full speed device has been connected. Similarly, a low speed device has a pull up on the D minus line. So when a low speed device gets connected, the host monitors the D minus line and finds out that it has been pulled up to 3.3 volt and infers that a low speed device has been connected. For high speed, it's little more complicated how the speed recognition is done. All the high speed device comes up as a full speed mode in the beginning, and then they go through a sharp speed negotiation protocol. So here you see this is the D plus D minus. This is the device side and this is the host side. So what's happening is, once the device gets connected, then the host drives a reset. That's both lines are held to 0, and any high-speed capable device will pull up the D plus line, drive a K-state on a D plus line, and this indicates the host that this is high speed capable. Now if the host is also high speed capable, it returns a series of KJ pattern here, and then both of the host and device are in the high speed mode. And if you see here that the swing changes from 3.3 volt to 440 or 400 millivolts, this is because change in the terminations in the drivers. Again, to support the on-the-fly plug-and-play feature, the USB host also must be able to identify when a device gets disconnected. So in a full speed and low speed mode, the bus is in the J state. That is, the D plus is high in full speed and D minus is high in low speed. So if the host detects an AC 0, that is both the D plus and D minus is 0 for 2.5 microsecond, it infers that a disconnect event has happened. Now for high speed, the idle state of the bus is AC 0 because it has a pull downs. The host has pull downs on both D plus and D minus in the high speed mode. So to detect a disconnect, it does a slightly different mechanism where a periodic SOF start of frame packet is sent, which has 40 bits of logic 1. And so if a device is disconnected due to impedance mismatch in the host side, the signal will be reflected from the open end of the cable, and this causes the voltage level to almost double. So there is circuitry in the host that detects the doubling of the voltage to detect that the device has been disconnected. It's a pretty neat feature and kind of interesting. Now let's briefly talk about how a USB 3 device is recognized. So USB 3 device has a 30 ohm pull down. The host polls for this impedance on this bus, and when there is no device, this is open and this link is in high impedance state. So this has a large time constant. However, when the device is connected, the bus is in low impedance and can charge pretty fast. So just seeing the charging capability of the line, the host infers if a USB 3 device is connected or it is in high impedance state. It comes to the address state where it has been assigned a unique address, and finally after enumeration and negotiation of the power budget, it comes to the configured state where it can actually start sending and receiving USB data. As you can see, there is a suspended state where if there is inactivity for a long time in any of these states, the device goes to suspended state, which is a low power state, and it's highly critical, as I mentioned before, because lot of battery power devices are using USB, and there should be a mechanism to conserve power. And when the bus activity is resumed, it comes back to the other working state from suspended state. Sorry, I have designed for 300 ppm, and if spectrum clocking is employed, the clock can vary from 0 to 5000 ppm. So certain redundant data called skip order sets are inserted for compensating the frequency of the transmitter and receiver. The USB 3.0 also employs equalization. This is a method to cancel the noise in the channel at the receiver. It uses RX receiver equalization, and actually a known data called training sequence is sent from the transmitter to receiver to identify the optimal filter parameters in the receiver so that it has a very low intersymbol interference. From a high level of data transfer, the USB device abstracts its functions as a series of buffers called endpoints, and the host actually addresses each device by its address, unique address, and the endpoint address. And logically, the link between the host and an endpoint is called a pipe. So this endpoint pipe model of data transfer is used in all versions of USB. Endpoint 0 is a special endpoint. It's called the control endpoint and is bidirectional, as you see here, and it is used for device configuration and management. And there could be a maximum of 16 input endpoints and 16 output endpoints. And one thing to note here, the in and out are with respect to the host. So in endpoints are actually for output from the device and input to the host, and out endpoints are input to the device and output from the host. This involves identifying the speed of the bus, and we have described that how the USB host comes to know about the device speed. The next step is enumeration, where the host resets the device, assigns the unique address, and reads the device descriptor. Device descriptor is a data structure in the device which gives the host enough information about itself, what kind of device it is, what is its power budget, whether it has a remote wake-up capability, how many endpoints, what are the kind of transfers it will support. Once the device endpoints are read by the host, it comes to know about the device and loads the appropriate device driver, and now the device is in configured state and it is good to send and receive USB packets. A little more detail on the device descriptors. As described, these are basically structures that are implemented in firmware to hold device characteristics, and it is read by the host during enumeration. There are several kinds of descriptors. The important ones are device descriptor, which gives details of what class of device it is, what are the protocols, and also the vendor information, who owns this device. And this vendor information, any vendor can register themselves in the USB implementers forum and get a vendor ID. The next class of device descriptor is configuration descriptor, which tells us about the different capabilities of the devices and the different functions the device supports, and then for each function it gives the number of endpoints, and then the endpoint basically describes the different kinds or direction of the endpoints, the maximum transfer size and maximum packet size. So as we have seen, a lot have gone into planning the architecture of the transceivers, from the cables to the ports to the receptacles to the connectors, and also into the data structure, so that the USB can support the backward compatibility and dynamic plug and play. Though it looks pretty trivial to connect and use an USB device, but there's a lot going on in the background that helps to make it function the way it does. Again, there are various kinds of devices. The important ones are HID device, which is a human interface device like the mouse and the keyboard, the mass storage device, which is like the portable disk drives, the communication devices, the Wi-Fi routers, USB connected Wi-Fi routers or modems or Ethernet ports, and there could be some special called vendor specific devices. And each device class needs a class driver, as we described earlier. So it has a special class driver which is a part of the device software, and also implemented, part of it is implemented in the OS. And different class of devices support different kinds of USB transfers and bandwidth. The first one is a control transfer. It is used for device initialization and management, and this has a guaranteed accuracy. All it means is error correction is done by retransmission. So USB packets have CRC codes, and this is checked at the receiver, and if the CRC does not match, then retransmission is done to correct the corrupted data. And control transfers takes up to 20% of the bandwidth. Very important kind of transfer is interrupt transfers, and this is basically used for HID devices to poll for data at regular intervals. Let me try to give an example where the interrupt transfers are used. Say you are using a mouse. So how it works is the USB host polls for the data from the mouse at regular intervals. It's actually 8 milliseconds, and the device driver and the software at the host, once read the data from the mouse, does the required functionality of moving the pointer in the screen. So interrupt transfers are very important kind of transfers, and one of the primitive transfers supported in USB. It has guaranteed accuracy, that is, CRC is checked and retransmission done if there is an error. And as you know, for a mouse to function, you need to get a steady data at regular interval, so certain kind of bandwidth is reserved for interrupt transfers. So actually 80% of the bandwidth is reserved in high speed, and this is shared with another kind of transfer called isochronous transfers, which are more real-time transfers. I'll come to it a little later. The next is the bulk transfer, which is used for sending large amount of data to printers or mass storage devices. Suppose you are taking a backup to your portable USB hard drive, it uses bulk transfers. So here there is guaranteed accuracy, that is, error checking is done and retransmission is carried out if there is an error, but there is no guarantee on the delivery time. It only uses the available bandwidth which is left after interrupt, isochronous and control transfers. Isochronous is a more real-time transfer which is used for streaming audio and video, and it uses a pre-negotiated bandwidth, and errors are detected but not corrected because it's a streaming service anyways, so it does not require correction of error, similar to the UDP in our networking. So I kind of went over how the USB bus functions, but just want to discuss it again, so the message is really conveyed well. All transactions are initiated by the host, and the packets are broadcast in the bus, and whenever the device gets a message, it checks if it is addressed to it, and if it is the device that the message is addressed, it will respond to the host transactions. And error checking is done through CRC, and there is also PID. We'll come to the PID in the next section, which is the packet ID, which also has toggle bits to detect error. Now USB is like a packet switch network. It uses packets to send data, and each packet has a packet ID, and there are several kinds of packets called token packets, which defines what kind of transfer will happen. The next is the optional data packet, which delivers the payload, and there's a handshake packet which reports the status. So the token packets are sent from the host to define what kind of transfer is about to happen. So there are several kinds of tokens: out token, in token, SOF token, and setup token. So out token packet is used for an out transaction. Again, the out is from the perspective of a host, so it is the host writing data to the device. The in token is host reading a data from the device. Once the in or out token is sent, it is followed by the data packet, which includes the data and the CRC, and then the source of the data or the recipient of the data sends the handshake packet with the status. So here is an example of a control transfer which uses the setup packet to identify that is a control transfer, and control transfers are always initiated from the host. Actually, any transfer in USB is initiated from the host, and then it sends the data, which is whether it has to program certain functionality in the device, and the device on receipt of the data sends the acknowledgement. So if there is some error, the device doesn't send the acknowledgement, and the host times out and retries the transfer. Similarly, for in transfer, where the host wants to read data from the device, it sends the in token to the device, This is followed by the data packet from the device and finally acknowledgement from the host. If the device is not ready, it could use a stall or NAC to identify the host that it is not ready, and the host can try the transfer later. And similarly, here we describe the out transfer. Another important concept in USB is the scheduling and USB frames. The USB host sends SOF packet every 1 millisecond. So all transfers are divided into frames, and in the high speed and super speed we use microframes, which is 125 microseconds. Now each frame is divided into different kinds of transfers, as we have discussed: isochronous, interrupt, control, and bulk. So isochronous are more real time, has priority and pre-negotiated bandwidth. So first the frame is filled up with the isochronous transfers, which is the video and the audio transfers, and then interrupt transfers, which also we discussed, which is like polling a device at a certain interval, which is also important and requires a dedicated bandwidth. And the isochronous and the interrupt transfer by themselves share about 80% of the frame bandwidth, and then the remaining bandwidth is assigned to the control transfers, and if at all something is available, it is assigned to the bulk transfers, which are not time sensitive, or like large amount of data sending to the printer for printing, or to the hard drive for backup. So USB 3.0 again, we discussed that had several improvements in the physical layer to support the high speed. Similarly, it also has some other improvements in the protocol layer to help manage the power and do more efficient data transfer. So the first is USB 3.0 is not broadcast, it is unicast. That packets are routed directly from the root port to target device. So other links can stay in the low power state. So the power consumption is minimized. Then there is an efficient token data handshake sequence. The less number of packets are exchanged to do the same transfer than USB 2.0. It also supports data bursting, where multiple bursts of data can be sent without an acknowledgement, and this improves the latency and performance of the bus. And as we mentioned, that USB 2.0 was a polled bus, where the host polls each device at a regular interval. But the USB 3 polled only once, and when the device is ready, it sends a synchronous ready signal and the data transfer continues. But in USB 2, if the device is not ready, it will poll again to see if the device is ready. And this is made possible because of the full duplex lines in USB 3, which is not available in USB 2, so it has to do regular polling. And there is some more handshake in USB 3 in the link layer, which also makes the protocol more efficient. Like all the token packets are subject to link flow control. So it uses a credit-based flow control, where the transmitter ensures that there is enough receiver buffer space at the link partner before sending a header packet, and all the header packets are error checked and sequenced at the link layer before it's sent to the upper layers. So as we have seen that USB is a pretty nice serial interface, and it has ubiquitous adoption in all device classes. There are some other competing serial interfaces, but none of them have become as popular as USB for different kinds of applications. I'm sure you're aware of HDMI, which also supports a similar data speed as USB 3, but it's mainly working with HD video and HDCP, which is the HD content protection, and PCIe is another serial interface, but it is mainly used inside the PC for connecting the peripherals, and SATA, which is used for disk drives. USB is also evolving, and there is a revision USB 3.1 specification released in July 2014, and it supports up to 10.0 Gbps, the 10 gigabits per second, and it is also considerably low cost when compared to Thunderbolt Lightning specification, which has also developed by Intel and currently being adopted in the Apple devices. So this will be a game changer for USB, and there will be new classes of peripherals that could get connected to the host using USB 3.1 specification. USB also coming up with a new type of connector. We discussed about type A and type B connectors. It's coming up with a type C connector, which is supporting the emerging devices which have much thinner form factors. And the USB type C connector can be plugged in any way. Currently the USB can only go in one particular orientation because of the placement of the USB 3 and USB 2 ports, but type C connector can be connected in any orientation. And as I discussed before, the new spec of power delivery coming, which can supply 100 watts of power for high power peripherals, and this will be very useful where we really do not need so many power supplies for all the peripherals, and it could be powered using the USB bus. USB is also working actively in a wireless USB standard and they have demonstrated wireless connection using USB, and the speed is similar to USB 2.0. Thank you for listening to my presentation. I hope you understood some of the points as how the USB bus is designed and how it functions. These are some of the references that I have studied in preparing the presentation and also referred to in my presentation. You can go over them if you are more interested in learning about USB, and if you have any questions, please don't hesitate to contact me. My email address is in the front page of the presentation. Thanks a lot.